Chapter 21 AP Environmental Science deals with global climate change, of course, one of those big-time environmental science. But let's dive into this. We know over time, over the last millions of years, of course, Earth's temperature has changed for many different reasons, particularly early on as our Earth was shifting and figuring out what to do during the Precambrian time and all the volcanic activity and so on. But even as of late, it's really been up and down. I'll show you some charts that show that. So we know temperature and precipitation really aren't fixed. We have volcanic emissions, we have different solar inputs, solar flares. Continents, of course, are moving due to tectonic activity. So we know we have global warming and global cooling periods. Of course, we have glacial times. We had glaciers around where we live, which is still shown. And we'll have more glaciers come in probably about 30,000 years, interglacial period. If we take a look at the last 900,000 years, you can see up and down in these charts. What that shows is we've got variance throughout. A little bit more realistic, in 22,000 years, we know that what happened was agriculture got established about 10,000 years ago. As a result of agriculture, what happened is we did a lot of slashing and burning, so cutting down forests and planting crops that we wanted to eat, and what happened is our temperature started going up. Well, realistically, what's probably happening is the temperature is going up because we've got carbon dioxide being released from the huge storehouse of temperature change over the last 1,000 years. If you take a look at it, again, up and down, but take a look as of late, particularly starting in the early 1900s, which really started our industrial revolution in the United States. It's going up, looking at the last 130 years. So since 1861 is when we really started looking at temperature data and collecting it officially. It's been up and down, up and down, up and down, and of course sometimes even around here we have warmer years, we have cooler years. And keep in mind this is global though. This is not just Wisconsin, this is the entire planet. If we have cool temperatures in Wisconsin one year, that doesn't necessarily mean in California they have cool temperatures. They might be having drought conditions, so it really varies. And we've got to look at it on a global scale, which is really hard to do. How do we know this is occurring? Well, the past 15,000 years, we can take a look at Antarctic ice cores. So they drill down into the ice, they can measure other levels of CO2 in there, figure out the temperatures based on that. Sediment cores, they can look at, so drilling down into the ground, pollen, fossils, coral, and actually take and really dig into the fact that climate has changed over the time. In the last, of course, over 100 years, I should say, 150 years roughly, since 1861, we've actually taken air samples in the troposphere and really keeping track of our temperature, and it's really gone up since then. In 1988, we had a very important committee formed. It was the Intergovernmental Panel on Climate Change, or the IPCC, and they evaluated changes. Now, the reality is we need heat, otherwise we would not be living on this planet. We'd be a very cold, lifeless planet. We have greenhouse gases. Think about a greenhouse like if you go buy flowers. There are greenhouse gases that keep heat in. These are molecules that hold heat. Carbon dioxide is one of them. That's the one that we think now, because of anthropogenic causes, is increasing our global temperature. Methane's another one. We get that from everything from rice paddies to the guts of cattle, of course, termites, landfills, coal production, natural gas leaks, and so on, and even rotting soil, bogs, marshes, things like that release methane. That is a global warming gas. Nitrous oxide, or N2O, generally from fossil fuel burning, big time from fertilizers. Remember, farmers need to put nitrogen on their fields, and what that's going to do is release nitrogen into the atmosphere and actually hold more heat. Chlorofluorocarbons from air conditioners, refrigerators, plastic foams, that is actually something that not only is a global warming agent or gas, but it also is something that we're going to talk about later. It's depleting our stratosphere of ozone. Hydrocarbons, or hydrofluorocarbons, are HCFCs rather, air conditioners, refrigerators, and so on, another greenhouse gas. Chlorofluorocarbons, or hydrofluorocarbons rather, and halons, which are from fire extinguishers, are the biggies. The big ones you really should know are carbon dioxide, methane, nitrous oxide, and CFCs. Throw halons in there. So the natural greenhouse effect, again, we need this. It keeps us warm. It warms our lower troposphere, and the surface is heated, and it's absorbed by water too and re-released later. Remember, water has a very high specific heat, so it absorbs that very well. We know there's a natural cooling process. Average surface temperature, now think about this. This is day and night, winter and summer, all seasons, is actually 15 degrees Celsius, which equates out to 59 degrees Fahrenheit. So that is our average temperature, and of course we are seeing that average temperature crawl up. The two major greenhouse gases, of course, are water vapor and carbon dioxide. So water vapor is just something that's naturally there. That's actually the #1 greenhouse gas. You know, when it's very humid in our region in the summertime, when you go outside and just kind of sweat, it's because there's a lot of water in the air. It's very humid, and that holds heat very well. So what happens is, of course, the sun's rays come down to the earth. Some, as soon as they hit our stratosphere, bounce back. But a lot of them, or some of them rather, not all of them, hit the earth. Some of it's absorbed and re-released later. Some of it goes back up, and what happens is all those little particles of carbon dioxide and methane and, of course, water vapor hold that heat and keep us warm. So what happens is we've got a very natural process, but are we actually adding on? Human activities, we've, of course, burning fossil fuels. Carbon is a very dense molecule of carbon, or coal rather is a very dense molecule of carbon. And what happens is when we release that, it releases all that carbon into the environment. Farming, of course, inorganic fertilizers like nitrogen. Burning forests releases our storehouse into the environment prematurely. Greenhouse gases are, we know, at the highest level in the last 160,000 years. Deforesting releases not only carbon, but also nitrogen too. Cattle, of course, landfill, add methane. The more meat that we eat, of course, the more cows that we have, the more methane they release. Cows have actually gotten the blame for this global warming too. And of course, fertilizers, particularly for rice, because we grow so much rice on our planet, adds N2O. 1 gallon of gas, by the way, does emit about 20 pounds of dioxide. So you can see there's no doubt that there's parallel between carbon dioxide and temperature change. The higher carbon dioxide goes up, as you can see it here, we also have higher temperatures go up. Are we contributing to this global warming phenomenon? We know that the Earth is getting warmer. Are we a big factor? The U.S., of course, releases more greenhouse gas per person than the rest of the world. We have about 4.6% of the world's population. We release about 24% of the gases. We also emit large quantities of methane, that's CH4, from landfills. So we throw a lot away. We're a throwaway society. Domestic livestock, natural gas, oil, and coal. You can see a little chart here. Carbon dioxide in the United States is going up since the late 1800s. With that is methane is going up, kind of stabilizing a little bit more because we have sanitary landfills. And what we're doing now, a very good thing, is we're tapping into that methane and pulling that out to make energy. That's stabilizing a little bit. Nitrous oxide, of course, is going up because, as you can see, that farmers putting nitrogen in their fields to grow crops. So here's the evidence according to the IPCC. In the 20th century, we know has been the hottest in the last 1,000 years. From 1861 to the present, our average temperature has gone up about 1.1 degrees Fahrenheit, about 0.6 degrees Celsius. Lake Michigan, since 1970, has actually gone up 5 degrees Fahrenheit, which is really high, and it's actually really disrupted their ecosystem. A lot of fish aren't living very well because their eggs can't handle that temperature change. The 16 warmest years since 1980, 10 warmest since 1990, and the hottest was in 1988. We know the glaciers are melting, they're shrinking. Their level has rose 4 to 8 inches. Keep in mind the reason that the sea level is rising is not because there's more water, it's because of thermal expansion. Those molecules are getting further apart and expanding. So global warming, temperature increases in the troposphere, changes in any aspect of the Earth's climate, like temperature, precipitation, and storm intensity. It deals with our global. A little chart here that actually shows the Arctic region, and this gets into something called the albedo effect. If you take a look at it in 1979, you can see how much area those glaciers actually covered up there. And now you can see in 2003, which is a little outdated, actually a lot is gone and diminishing. The big is Greenland, which we'll talk about later, that we're freaking out about. Keep in mind that glaciers, volume for volume, are not going to increase sea level because they're already there. Think about an ice cube in a cup of water. It's the same amount of volume. So this is something called the albedo effect. Albedo, think about it as reflecting. Clouds have about a 50 to 55%. Albedo affects snow about 80 to 90%. That means snow reflects about 80 to 90% what hits it back. That's a good thing. Cities about 10 to 15%. So a lot of cities absorb a lot of heat. Bare sand about 30 to 60%. Oceans only reflect back about 5%. So a lot of it is this heat is absorbed in the ocean. Now what's happening with the albedo effect, as our Arctic regions are melting, we have less albedo effect. So this is a positive feedback loop. We have less reflectivity, which means our Earth is absorbing. So, as we just said, the albedo effect comes into play. We've had the greatest increase in temperature in polar regions. It's an early warning sign. Floating ice is melting faster than it's formed, which is really have a devastating effect on the polar bears in that region. Half of the Arctic ice is probably going to be gone by 2050. If Greenland melts, this is the biggie, because that ice on Greenland is on top of land. That's going to melt into the oceans if it all melts. Sea levels are up 23 feet, so say goodbye to regions like New Orleans. And a lot of that eastern part of the United States, as a matter of fact, even up into through Georgia. Glaciers, of course, are melting at a very fast rate in Alaska. Permafrost, which is, of course, when the ground is frozen, like in Greenland, is warming and melting in Alaska. Buildings, pipelines, utility lines are actually sinking up there along with that, too. As it's melting, they're getting more bugs because they can live in those regions. Everything is basically shifting. Our biomes are shifting because of this. Mount Kilimanjaro in Africa may be ice-free within 15 years. Loss of frozen water means loss of reservoirs of water for warmer months. Keep in mind, lots of regions, even in the United States, rely on this water runoff for their drink. Today's sea level, of course, it fluctuates up and down, but of course, in the last probably 25,000 years ago, you can see how it shot up again due to thermal expansion. Those molecules are. If the Arctic ice melts, sea level may not rise. Weather patterns may shift. Reduce wintertime precipitation, in other words, less winter melt for the southwestern United States, as I mentioned. Alaska's really had the most noticeable effect. What happens is we've had huge releases of CO2 and CH4 up in those regions. What happens is land melts. What happens is it becomes kind of a bog, and we get anaerobic bacteria that releases methane gas into the environment. The thing is, they've actually got longer growing seasons in Alaska now, and we've seen that as of late. If you look at climate in the last few years, Alaska's climate actually suffers in the wintertime. So how do we project future trends? That's a big question. We can use 3D models of energy flow. We can use air masses, moisture flow. Models, according to the IPC, we have evidence that the last 50-year increase is anthropogenic. In other words, as we deforest, as we burn more fossil fuels, we know that's contributing to this. No doubt carbon dioxide is holding heat. Between 2000 and 2100, we're looking at a 1.4 to 5.8 degrees Celsius increase, which will be. You can see the projected increase here using models. We kind of need to stop this soon. What happens is if we go up, we could reach that 5.8 degree temperature by 2100. If things go as they are now, by 2050, we're going to have the climate of St. Louis, which is much warmer than we're used to. So all our plants, everything will shift. Results of temperature change: alter the rates of precipitation or evaporation, alter wind patterns, alter ocean currents. We've seen increased storms in the New York region, the Connecticut region. That warmer temperature is causing those storms. Remember, we don't have more hurricanes now. We've actually got more intense hurricanes like Hurricane Katrina. We might have to shift where our food is grown. It may alter sea levels. We're going to increase drought and floods. You can see the patterns here, and of course what we're seeing now is increased patterns of warm water actually coming up through the northeastern part of the United States, which is increasing that region. Scientists, of course, can use circulation models. We know according to the IPCC, latest climate models match the records of global temperature changes since 1850, so their models are pretty much on track from what's actually been occurring. New and stronger evidence that most of the warming in the past 50 years is, of course, due to us. It's likely the Earth's surface will increase quite a bit, 2000 and 2100. Ocean waters do absorb CO2 and heat. That's a very good thing. They store it as carbonate ions. But will they release more? It said the oceans are about 80% full right now. And what happens is once they're full of those carbonate ions is they're going to start releasing it, and of course that's going to be a positive feedback, and it's just going to make our global warming increase at a phenomenal rate. Global precipitation patterns are going to shift. We already see that happening. Tropical oceans are saltier than polar oceans were 40 years ago because of evaporation rates. Increased CO2 may increase photosynthesis. Maybe warmer air may release COH4 from bottom too. One thing is aerosol pollutants. It used to be much more common, particularly with CFCs. CFCs were chemicals that were like in hairspray bottles, and they're actually very explosive. What happens is we have a ban on that due to Montreal Protocol, which is a good thing. It can warm or cool the atmosphere too. Soot, especially, think about smoke, the soot from smoke. It could block the sun's rays from coming in, or if it allows the sun's rays from coming in, it may hold it from going back out into space. We do have warmer nights produced from clouds trapping heat. Pollution, of course, dim sunlight. Maybe that's going to affect how our plants grow. Again, maybe affect our agriculture. Who knows? Aerosols are not a major problem as they were before the Montreal talk stratosphere a little bit more. Increased CO2, of course, could increase photosynthesis and remove CO2. That's a good thing. Maybe plants will help absorb that CO2 as long as we don't keep cutting them down. Old growth forests and rainforests are experiencing rapid changes because of CO2. Remember, plants need CO2 in order to respire. When the old trees die, of course, what happens is that decreased CO2 is absorbed. So what happens is the old trees, all that old growth dies. And of course, eventually that, when it deteriorates, that CO2 is going to be released in the environment and of course cause yet another positive feedback. All right, that's it for part one. We'll continue on with our last one soon.